Hi. Welcome everyone to another episode of Solidity Fridays. I am joined with Tamara and Matt today, and we are going to be looking through Ultra Secure's multiple flash swaps on Uniswap V3.
Yeah,
So yeah, Tam, over to you.
thanks.
Hey guys.
Hi Matt, how you doing?
Yeah, not bad, thanks. How are you?
Yeah, good, thanks. Matt's joining us today. He's a Solidity developer and a Rust developer and a good friend of mine, so I'm quite excited to do this. Yeah, we found this repo. It came out about 3 months ago. It's by Ultra Secure ETH, but it's on Contago. I think that's how you say it, Contango. On their repos. I think he works for them, and if we have some time, we can look at some of their stuff too. Yeah, really cool profile picture, and we thought it would be quite fitting for Easter.
Yeah, definitely.
Interestingly, for a really good Solidity developer, a lot of Scala and Java pinned repositories. Yeah. And here is their Twitter, should you want to follow them after seeing this cool code. All right, so let's dig in. Maybe at the README. So it's Uniswap swap router re-implementation to allow for flash swaps involving multiple pools, and we'll see how he does that. I think it's a he, but I'm not sure. I'm just going to say there. So there's a flash swapper, and it works very similar to Uniswap's swap router. The main difference is that the calling contract should implement iFlash swap caller. Sorry, iFlash swapper callback to handle the flash swap. Only calls from flash swap are allowed to protect the callback method, and we'll probably look at the tests to see a working example, which is exciting.
Yeah.
Interesting. It's they used Soulmate and not OpenZeppelin. That's
Zeppelin.
fun.
Yeah.
Cool. Let's dig in.
And also using
My
Foundry
Catchup is
instead of.
frozen.
Oh,
Yes, and like using Foundry, which is cool.
Yeah.
This is frozen. Sorry, you guys. Let's reload that. I'm surprised I can still stream. Sorry, this has never happened before. There we go. Cool. Maybe we start by looking at the dependencies. What do you think, Matt?
Yeah, sure. Let's do that.
Cool. So there's one contract called Uniswap.sol. It's probably everything that they need from Uniswap in one. Yeah.
Yeah, makes sense.
Yeah, that's nice. Is the dark mode okay? I know you're a dark mode person, but is this okay?
Yeah, no, it's cool. Yeah, no, it's great. Yeah, thank you.
Okay, cool. So it imports Uniswap V3 pool, and that's it. That'll be in the lib folder with the remapping probably. Cool. The tick math library just for doing tick operations. Library pool address. It's got an internal constant variable and a struct pool key, which has 3 entities: address token 0, address token 1, and UN24 fee. And these functions get pool key. Yeah, it probably returns the struct. Yeah. It's
Yeah,
internal
looks like
and
it.
pure.
Yeah. Yeah, so this would be a linked library because the functions are internal. So you're going to have to, as opposed to an embedded library where functions are generally external, if I'm not mistaken. Oh, no, I'm confused. It's the other way around, if I'm not mistaken. I think embedded,
Okay.
I think it's the other way around.
So this would be an embedded library.
Yeah, I think so.
Okay, yeah, I think that makes sense.
Yeah.
My cat's trying
Makes
to open
sense.
the window, but I'm pussy, and hopefully he gets over it. Otherwise, I'm gonna have to move him out. Sorry. Cool. Yeah, so it returns pool key, the ordered tokens with the matched fee levels. And then there's another function called compute address, also internal, that deterministically computes the pool address given the factory and pool key.
Cool. Yeah.
Right.
Looks like hectic nesting there.
Yeah, gosh.
Yeah.
So it's is there a library used for casting? No, I don't know if a library can use
Casting.
another library. Yeah, so it's encoding the token 0, token 1, and fee of the key,
Yeah.
which is from that struct pool key.
Yeah.
Encodes those with ABI encode, then Catchup hashes those, and then along with the hex FF factory, which we've passed in, which is an address of the Uniswap V3 factory probably, and the pool init code hash, which is this
The initial one. Yeah. Yeah.
Interesting thing, I think it has to be a constant variable in a library because if it was immutable, it couldn't get set because there's no constructor in a library.
Yeah, and you can't have, it doesn't have state either. So
Yes,
you
yeah,
can't
so you have
have,
to keep
yeah.
constants. That's correct.
Yeah.
Then they then they ADI encode packed all these things, and then Catchup hash 256 those.
Yeah.
Cast that to a uint 256, and then cast it again to a uint 160, and then to an address.
Interesting.
Very interesting. Oh, library path. This is probably where they get the like the paths for the multi, like for different pools if there's multiple pools. So as you can actually use a library inside a library using bytes lib for bytes. That's cool.
Cool. Yeah.
Cool. Some constants, mainly just offsets and sizes. Function has multiple pools. Gets if the path length, so it takes in a bytes path, and it says if it's multiple pools min length, which is up here probably pop offset plus next offset. Also pure because it doesn't read or write from storage. I mean, cool number pools, also internal and pure. Takes in the path and returns the number of pools in that path. That's cool.
Yeah.
Decode first pool, returns address token A, address token B, and UN24 fee. So this probably just finds the gives you the details of the first pool as a pool key struct maybe.
Key. Yeah.
But actually, no, it doesn't. It gives you the entities of the key. My bad.
Oh, right. Yeah. Because you saw that in the first struct, I think.
Yes, we did.
Yeah.
So it just returns those. And I love it when there's no return statement. It just, you say it returns address token A, and then you set token A, and it knows to return it for you.
Yeah, that's cool.
Get the first pool. This is in bytes memory, and this is the segment corresponding to the first pool in the path. Skips the token and a fee element from the buffer and returns the remainder. Okay, that's quite cool. That he has the bytes lib that we're using in this above library. I don't think we really need to go into how they're doing the byte manipulation.
Yeah, there's some assembly there.
Yes, there's some assembly here with a switch, and
is there a default case?
There must be.
There must be, yeah.
There it is. Nice.
Ah.
Yeah, I don't think you can have a switch without a default.
If
we want a zero length slice, let's just return a zero length array.
Yeah. Cool.
Yes, and obviously M stores are not S stores because we're using memory because we're a library.
Yeah.
To address, we saw that above, 2 and 24. Cool, and then this looks like it'll be important. Library callback validation provides validation for callbacks from Uniswap V3 pools. There's two internal functions, and the first one returns the address of the valid Uniswap V3 pool, and the second one does the same, but it has a few less parameters. So it's overridden. The first one takes in a factory address, which is the Uniswap V3 factory, token A and token B, and the fee.
Yeah.
It returns what pool that is.
Cool.
By calling this function, passing in the address of the factory, the pool key, which they make using get pool key, passing in token A, B, and fee. And then, they pass those two things in, which returns the pool by going pool equals iUniswap v3 pool. So they make it a pool instance of that interface. They compute the address they compute the pool address using the factory and the pool key. And then they make sure that message sender is equal to the address of the pool. That makes sense, because we want to verify that the callback is from Uniswap itself, not from, balancer pool or something. Okay.
Yeah.
Awesome.
Cool. That looks cool.
Interesting. We didn't see any swap stuff that might be in their code. Maybe interfaces next.
Yeah, let's do that. We can check out the NAT spec as well.
Yeah, I'm getting the vibe that the NAT spec will probably be in
useful.
Here.
We have a question. Just when would this be useful over the standard Uniswap router stuff?
Well, because this is flash swap, so it's you can do multiple pool swaps in one go and in one transaction.
Right. Yeah, pretty cool.
Nice to have a question.
Yeah, that's a cool question. Yeah.
Cool. Good thing we're looking at this interface. This is the iFlash swapper, because it's got some struct. Cool. This is the router.
There's a follow-up question. But doesn't the router do multi-hops?
Yes, but they aren't flash swaps.
Flash swaps.
I think. Hopefully they reply and enlighten us. In the meantime, so this is for exact input single params. So that's the struct, and basically, if you're doing an exact input swap, you use these params. So this so far is like standard Uniswap stuff. An exact input means, like, if I'm swapping USDC for ETH, I want to use exactly 10 USDC for as much ETH as possible, as opposed to an exact output swap.
Yeah.
Cool. Then there's the exact input single function, external. Exact input params. So this is for a multiple pool swap. It takes in the bytes path. Cool. And then there's a function that uses that param to do an exact input swap. Exact output single param. So an exact output swaps as little as possible for the USDC for amount out of another token. So if I want to get one ETH out, then it uses as little as possible as USDC to make sure I get exactly that amount out.
Yeah.
And then they have the same for multiple pool one with taking in the bytes path. Right. Yeah, cool. And it's encoded in call data. All of these parameters. Cool. And then there's another interface called iFlashSwapper callback, and it has one function that any contract that calls any function on iFlashSwapper must implement this interface. We saw that in the
Yeah.
The callback is called after the flash swap is executed and must pay the owed amount to the pool. The callback implementation should check for slippage and revert if the slippage is unacceptable.
Yeah.
Cool. So there's a function called flash swap callback, and called to message sender after executing a flash swap via iFlashSwapper. In the implementation, you must pay pool tokens owed for the swap. The caller of this method must be checked to be the same instance of iFlashSwapper that was initially called here. It takes in amount received, the amount that was sent to the calling contract as proceeds of the flash swap, amount to repay, the amount that the callback must send to the pool, the address of the pool that is owed for the amount to repay, and bytes call data, any data passed through by the caller via the iFlashSwapper data parameter. Cool. How are we doing for time? Right. Might be a bit of a short episode this one, but we can also look at his tests, all their tests.
Yeah.
Cool. Yeah, so we're using SafeCast by Uniswap and Safe Transfer Lib by Soulmate, which is cool. Not the
Yeah.
open
Zeppelin stuff.
I haven't actually really looked
Yeah.
at the Safe Transfer library. I want to check it out.
It could be cool. Yeah. I haven't looked either.
Cool.
And then there's just a Uniswap dependency from earlier.
Yes.
The libraries.
Yes.
Yeah.
Contract Flash Swapper is iFlashSwapper. Uses a few libraries. So yeah, we're using Path for bytes, SafeCast for UN256, and Safe Transfer Lib for ERC20s. Internal constant address factory with the Uniswap V3 factory. Struct swap callback data. So it takes in the path, the address of the payer, the recipient in the first pool, the amount received and the amount to repair, and bytes user data, which I think is, you can just put an empty string there, or empty bytes. Cool. Uniswap V3 swap callback. I think that's just like a normal Uniswap V3 swap callback. Oh no, wait, we saw this in the dependency here.
Yeah.
So takes in amount 0 delta, amount 1 delta, and bytes call data, external override. Require that the amounts are greater than 0. So swaps entirely within...
Well, yeah. Sorry.
Oh, I see. Sorry. Either
It's the delta.
Yeah, either delta must be greater than 0. Swaps entirely within 0 liquidity regions are not supported. I see. Thanks.
Yeah.
Catch.
Yeah.
Cool. Swap callback data memory. Callback is ABI decode the data, passing in the swap callback data.
Cool.
Then we go callback. So now we have this callback data. We get the path, and then on path we call the code first pool, which was, we saw that function, I think in our dependency, yeah. This returns the address of the token in, the token out, and the fee of the first pool in the path.
Yeah, so that was from the pool, the pool key.
Yes, they get this from the pool key.
Yeah,
That's correct. And then they do a callback validation, and they verify the callback, passing in these parameters they just got and the factory address. Then, if
Jeez.
count 0 delta is greater than 0, we do line 35, and we first say if token in is less than token out, then we get a bool is exact input. Then we cast amount 0 delta from being an N256 to a UN256. That's amount to repay. And then so now if this is greater than 0, that means this passed, and this isn't necessarily greater than 0. So we get like almost like its absolute value, and then we cast it to UN256. But if amount 1 delta, so if amount 0 delta is less than 0 or equal to 0, then the bool is token out less than token in, and we cast UN256 in amount to repay. It's actually the amount 1 delta, and amount 0 delta we negate it and then cast it to UN256. So it's basically seeing which way it's going.
Yeah, geez, that's a really complex ternary.
Yeah, it is quite a complex ternary. Cool. Then it says if the first pool is address 0, then we make message sender the first pool, and we set in the callback data here, we set amount received and amount to repay. If it is an exact input, the caller must pay to the first pool in the chain. Additional pools are paid by the previous pool. So it first sees if the first pool is not equal to message sender. So basically that means this hasn't happened. Then we do a safe transfer of token in from message sender to message sender amount to repay. But if there are multiple pools, we need to sell the received amount to the next pool in the path. So if path has multiple pools, then we skip token and do an internal call to exact input, putting in amount received is amount in, and the recipient is either address this if it has multiple pools, or if it doesn't, then the recipient. And data is that callback data that we made right at the start of the function. Else, so now if it's not the exact input, then oh no, wait, sorry, this is actually else for this. So if it doesn't have multiple pools, so if there's only one pool left in the path, then we can call the callback. The funds were already sent by the last swap. Cool. So then we go cb.payer, and we so I flash swap a callback. It's not an easy one to say quickly. Passing in a cb payer address. Then we perform a flash swap callback, passing in the amount received, amount to repay, pool, and data. And then else, if it so now it's not exact input. It does the same thing. It says if it has multiple pools, skip token, and if there are multiple pools, we need to buy the repayment amount from the next pool in the path. So then we do an exact output, passing that in. But if it's the last pool, or like there's only one pool left in the path, then we can call the callback. The funds are already sent by the last swap, and then that's where they perform the callback over here. So it's more or less what we've seen above, but just with the exact output and not exact input.
Yeah.
Cool. And then now we see the how exact input actually works. It takes in those params that are defined in the interface for iFlash Swapper, and it performs an exact input swap on those params. And then it also does a swap callback data with the path and payer recipient first pool being address 0, amount received 0, amount to repay 0, and user data is params.data. Yeah, exact input. This is if it has multiple pools. Yeah, and then this is the actual exact input. Function. It's private. I thought it was internal, but it's private.
Oh, yeah.
Cool. So it takes in an amount in, a recipient address, and swap callback data, memory data. Data.path.decode first pool gives us a token in, our token out, and our UN24 fee. So we first see if token in is less than token out, and if it is, this 041 is true. Then we get pool, passing in token in, out, and fee, and then in that pool we call a swap, passing in the recipient, the bool, amount in to int 256, and then if that bool was true, then we do tick math.square root ratio +1. But if it is false and token out is less than token in, then we do tick math.square root ratio -1. And then ABI encode data. All right. And then this is where this actual swap happens.
I'm interested to see, so if you scroll up, because we're dealing with just down the exact input. The bool 041 is equal to token in, it's a bit blurry, less than token out. What would be the case if they're equal? Would that, I suppose it's not really possible, would it, if you're dealing with an exact, because we've got here, because we've got your 041 is equal to token in less than token out, and then in the ternary, no. Sorry, I think I'm misreading this. 041. Oh, it's a bool.
Yeah.
Oh no. Yeah. Okay. Sorry. Yeah.
So if they're equal, it won't.
Yeah.
It'll be false.
Sorry, it was a bool. Sorry.
No, it's true. But yeah, I don't know if they would be equal. Likely.
No, it's not possible. But yeah, sorry. I was just thinking. Yeah, it's a silly question. My mind was just trying to think up any possible case, and there's only really 2 possible cases in that case. So,
anyway. Cool. This is the same, but an exact output swap. And they call swap callback data. Oh, they pass in swap callback data, which is all this. And then here's another exact output swap with a path for multiple pools. Cool. Then this is the same as the exact input, but we're performing an exact output swap. And there's one more function that's private and pure called get pool. Returns the pool for a given token pair and fee. The pool contract may or may not exist. Cool. Awesome. Should we look at the tests maybe?
Tests. Yeah. Oh, I'm excited. It's going to be in. Oh, yeah. Yeah.
Yeah. I love looking at tests in Solidity. So much nicer. Cool. So we have some constant addresses. DAI whale, USDC whale, WETH whale, Bitcoin rat whale. Expected data is data. Bob is address OX Bob. So we have our test address, then an internal flash swapper instance called flash swapper. Cool. Then the setup, virtual VM.make persistent, so we're making Bob persistent. Then we select a fork, they're doing mainnet. At this instance, we label our coins, basically our tokens, and then we make a new instance of the flash swapper. Test exact input single direct. Cool, so we make a new caller with USDC and a USDC whale. Then we make params for an exact input single swap. Then we prank with the address of caller. So the next call is by them, and we do an exact input single swap, passing in params, which are these above. Then we assert equal decimal. So we're making sure that WETH is 18 decimals, and that the balance of Bob is this much ether. Then we check that the data is equal to the expected data, which it will be because we pass it in here on line 47.
Okay. Yeah.
Then we do the same assert equal decimals with amount received and amount to repair. And because we're doing a USDC WETH swap, amount to repay it's got 6 decimals for USDC and 18, and then 18 decimals for the WETH. And then we check that the amounts are correct. Cool. Test exact input single reverse public. Obviously public, it's a test. Cool. Make a caller. Make exact input single params. Cool. It's similar to the above one. Then we prank as address caller, and then the address caller performs an exact input single through the flash swapper. We assert that USDC that we have the correct balance and 6 decimals. We assert that caller.data is expected data, and that so now we're swapping the other way, and we make sure that amount received is this
6 decimals.
6 decimals and 18 decimals for ETH, or wrapped ETH.
Yeah.
This is with one pool, so it should be more or less the same. We just don't have that. I see, we have a path. So we make a path because the path's always bytes, so we go abi.encode packed with UNT 24500, because that's the fee. And USDC, recipient Bob, amount in 1 ether, and because this will be exact input, so we're trying to use this 1 ether fixed to get as much USDC out as possible.
USDC.
Cool. And then some asserts. 2 pools. So here we have the path is, and I think the paths happen in reverse, if I'm not mistaken. So let's check that. So we're using 1 ETH and we're trying to get out. Yeah, amount received is USDC. So actually, no, it goes like this. Yeah, I'm putting this in, and I want to get that. So it's not actually reversed. Cool. So the difference when it's 2 pools is on line 106 with the path, where it goes WETH. This is the fee to USDC to this is the fee, and then to DAI. And it's an exact input. All we know is we want to swap 1 ETH for as much DAI as possible via a USDC. And we make sure we got the DAI and that we have 18 decimals. This is the same but in reverse. So we start with DAI. We want to get WETH. 3 pools to eventually end up with wrapped Bitcoin. 8 decimals and 18 for the ether. 3 pools reverse, so we want to end up with WETH. So amount to repay was 8 decimals and amount received is 18 decimals. Okay, and then let's test exact output single direct. So it's just a normal single pool swap. Yeah, and that's in reverse. One pool. Okay, so these are all the exact output swaps now. So we know how much we want out, and you can use as much
USDC as you
yeah.
want.
Or the goal with an exact output is you know what you want out, and you want to use as little USDC as possible, but
Yeah.
you don't mind
Yeah.
how much is actually used. Two pools. Okay,
Yeah.
I think we get it. It's very similar.
Yeah, I think they are quite meticulous with sort of one pool, two
Yeah, it's
pools,
very
three
good.
pools, four pools.
Um,
It is, yeah.
oh, and here's the
Yeah.
caller. Because yeah, we saw the caller implemented in the setup. No, in the functions themselves, not in the setup. It is iFlash swap a
Yeah.
callback. So this would, yeah, this would be done by contract and test token in whale data amount received. Cool. So this is all, yeah, these flash swaps are all done by like smart contracts, not by individuals, like not by EOAs. Cool, and it has this one function which is external and override. Takes an amount received.
Yeah, that's the one required.
Yes,
Yeah.
it is. Amount to repay, address pool, bytes call data. Prank is the whale, and transfer to the pool, amount to repay, pause gas metering, data equals data, amount received, and then you resume gas metering. That's interesting. So they're checking how much gas they're using as they go, but not here.
Yeah, the comments also Ben also mentioned that. It's cool.
Yeah, that's really cool. Awesome. A bit of a shorter episode today, but I think it was quite cool to see. And
So just for like the more of like a layman interpretation, so the benefit of this is that you just don't have to look at the cap, like you don't have to put in your own capital in order for it to happen.
So these flash swaps can be done by a smart contract. So a smart contract can do like multi-pool swaps, which you can do with Uniswap, but it's done in a flash swap. So it's like really efficient and done in a single transaction, I think.
Okay.
Yeah, you can do multiple. Yeah.
Yeah. So I think I'm saying it right. Ultra secure, cool stuff. There's their Twitter again, and yeah, this was done in the Contango repo, and they have some other cool stuff which would be quite cool to look at one day. But yeah, let's go back here.
Cool.
Awesome. Thanks, Matt, for joining
Alright,
me,
then.
and thanks,
Yeah, it's been
Rebecca.
interesting. Yeah. It's been really interesting.
Yeah, thanks guys.
Yeah.
And enjoy the holidays. Happy Easter.
Yeah.
Yes. Happy holidays and whatnot.
Bye. Thanks guys.
Thank
All right.
you. Bye.
Bye.